All right, here we go with thermochemistry. Let's start with the definition of thermochemistry, which I have written here. It's the branch of chemistry concerned with the quantities of heat evolved or absorbed during chemical reactions. And so we'll be talking about things that are going to be endothermic or exothermic, meaning they give off heat or take in heat. So take a few minutes to write this definition down before you move on to the next slide. So one of the laws we'll be dealing with in this unit is the law of conservation of energy, which is similar to the law of conservation of mass. And that law states that energy can neither be created or destroyed, but it can be converted from one form to another. Oftentimes it's actually converted to an unusable form, which is why there's all this push about renewable energy sources, because once we burn hydrocarbons, the energy is changed over to a form we can't use. This law is known as the first law of thermodynamics. Heat is something we're going to be talking a lot about, and it is represented by the symbol of a small q, and it is energy that is in the process of flowing from a warmer object to a cooler object. That's an important thing to remember. It always flows from warmer to cooler. When the object is losing heat, the temperature decreases, and when the cooler object absorbs the heat, obviously its temperature rises. So we'll be talking about three types of heat transfer. First type we're going to talk about is conduction, and the definition for conduction is two substances in direct contact, and so the heat is transferred because they are directly touching each other. So let's say we wanted to boil some water on the stove. The metal pan on top of the stove would be conduction. Convection is the transfer using density-driven flows, which would be in fluids. And recall that fluids are liquids and gases. And an example of that is a heater in your home, because the warm air is being blown out and it mixes with the cold air. And because of the difference in density between the warm and the cold, it mixes and actually warms your home. And then, of course, the third type is the sun. We feel the radiation from the sunlight. That's often how we get sunburns, especially if some of you came back from spring break with a sunburn. That was due to the radiation traveling from the sun. Here's a few more examples of the conduction, convection, and radiation. And of course, right here we have conduction because we have direct contact with the heat source and whatever he's holding. Convection is where it's the mixing of the airflow, and you see the warmer and colder arrows here because that's how they mix. And notice this is not in direct contact, it's the air right above the Bunsen burner. And then this last one is some sort of special lamp, probably some sort of heat lamp or sun lamp, and it's being radiated throughout that. That's also the way that tanning beds would work for those of you that do that, although I highly suggest you don't do that. It's very unhealthy. And then we have one more example using a campfire on the next slide. So in this slide, I want you to stop and think about looking at this campfire and the roasting of marshmallows, and think about the three types and see if you can come up with examples of convection, conduction, and radiation. So what I came up with is, obviously we have the direct contact of the metal. So if you were to touch that metal near the marshmallows, then of course it would burn you. And then the convection, of course, would be those kids that are sitting around the campfire. They would feel the heat of the fire and the warmth of the fire, and so that would be convection. And then of course the radiation is you can actually see the hot coals radiating the energy from them. Now that we've talked about what heat is defined as and how we have three different types of heat transfer, let's talk about how we're actually going to measure heat. Before we can do that, we need to define what a calorie is. And as you can see from this definition, a calorie is the amount of heat required to raise the temperature of 1 gram of pure water by 1 degree Celsius. And we call that a calorie, which is a little different from the food calories. When we talk about a granola bar having 150 calories, when we're talking about food calories, that's actually a kilocalorie, and that's designated with the capital C. If we're talking about the SI unit of heat and energy, we're going to be using something called the joule, which is a capital J. And in this case, 1 joule is the equivalent of 0.239 calories, or 1 calorie is equal to 4.184 joules. So in order to measure heat, we're going to definitely need to know the temperature, and so we need to define temperature, of course, and that is the measure of the average kinetic energy of the particles. And we've talked about this before, how temperature and kinetic energy are directly related. In the gas law unit, we talked about heat 'em up, speed 'em up, and of course if you heat particles up, the temperature increases, and that means the particles move faster, which is also going to increase the kinetic energy. We will be measuring temperature in either Celsius or Kelvin, just like we did for gas laws, we used Kelvin. Most of the time we'll be using Celsius, but you also need to understand that we can have temperature measured in Kelvin as well. So this is a very important concept to remember, and a lot of times students get confused, and we need to know that heat and temperature are not the same thing. So put a star by this slide so that you can remember that for a test. Heat and temperature are two different things. All right, so another thing we're going to need to be able to calculate heat is specific heat, and that is the amount of energy that is required to raise the temperature of 1 gram of pure water by 1 degree Celsius. Now, specific heat are values that we can look up in tables, and they are specific for whatever material is being used. So in this case, water has a specific heat of 4.18 joules per gram times Celsius. And you'll see on the next slide that we have several other specific heats listed for some other materials. And the reason there are so many different specific heats is because different substances, of course, have different compositions. So each substance has its own specific heat. And again, these are things that we can look up in a table, or if we're working a problem, we may give it to you already so that you don't have to go look it up. So as we're getting ready to calculate the specific heat, we need to remember that it is the heat absorbed or released by a substance, and it depends not only on the change in temperature, but it also has the specific heat, and we're also going to be needing the mass of the substance, and that is going to all be used in a calculation. We use something called a calorimeter to measure the heat changes, and it's something that minimizes the amount of heat lost to the system. One common one is called a coffee cup calorimeter, where we do 2 coffee cups nested in each other, and of course it's insulated. And so it reduces the amount of heat that's lost so we can measure it more accurately. So here's the formula for calculating specific heat. Q is the amount of heat lost or gained. C is, of course, the specific heat that we talked about on the previous slide. The little m is mass, and delta T is your change in temperature. It's worth noting that you can rearrange that equation just by putting the mass and the specific heat and delta T in different order. Sometimes we like to do that, and we call that the MCAT equation because it kind of looks like MCAT. And before we get into the calculations, I want to make note that if Q is a negative value, that means that heat was released from the system. In other words, it went out of the system. And that if Q is positive, then that means heat was absorbed. And we'll get into that on the next unit, whether that's going to be endothermic or exothermic. But for right now, Q negative means we released heat, and Q positive means that we absorbed heat. So here we have the equation explained a little bit more thoroughly. And again, Q, heat absorbed or heat released. And remember we said if it's absorbed, Q is going to be positive. And if it was released, it's going to be negative. So we need to remember that. The specific heat of the substance, and that is what we look up in the tables. And remember the units of that is usually going to be joules per gram times either degree Celsius or degree Kelvin, depending on how the temperature was measured. M is got to be in grams because of this G in the specific heat unit. And then T, delta T, is the change in temperature. And we always want to make sure that we remember that it's T final versus T initial. Okay, because that right there is going to be where our positive or negative comes from, because obviously if we decrease the temperature or increase the temperature, it's going to change the sign of that delta T. So let's get ready to do a calculation. So this problem says how much heat is given off when an 869 gram iron bar cools from 940 degrees Celsius to 50 degrees Celsius. And so before I even go work the problem, I want to look at a couple of things as a clue word to know should my Q value be positive or negative. And the fact that it says heat is given off, that means heat's going to be released. So I should expect a negative number. And also I can see that if I went from 940 to 500, that I obviously released energy or released heat to get that to cool down. And so I should expect my value to be negative as I'm going through this problem. And of course, let's get ready to do this. So C, which is our specific heat for iron, is 0.444 joules per gram times degrees Celsius. We found that in a table and gave it to you. That is something you can look up. The mass it gave us from the problem was 869 grams, right here and right here. And then our T final minus T initial for our delta T. Our final temperature was 500, so we subtract 940 and we get a final temperature, or not final temperature, excuse me, a delta T of a negative 890 degrees Celsius. So now we simply plug everything in. So here we have our C value right here, our mass value right here, and our delta T value right there. So then it's just a simple multiplication problem, and we multiply it, and we get our final answer of negative 343,000 joules based on our significant figures of needing 3. Okay, and we did expect our value to be negative when we started, and we ended up with negative, so we can kind of just double check ourselves and make sure that we have the right sign, whether it's positive or negative, depending on what happened in the problem. All right, stay tuned for the jokes. If you don't want the jokes, stop the video now and you can get started on your homework. So I went to the rodeo yesterday, so this made me come up with some cow jokes to tell for this video lesson. So here we go. What do you call a cow with no legs? You call it ground beef. What do you call a cow with 2 legs? Lean beef. And what do you call a cow that has just given birth? She's decaffeinated. And then the last one, why should you never ever tell a cow a secret? Because it goes in one ear and out the other. All right, guys, you have a great day.